Let me ask you something. Where do you actually think gold comes from? If you have never had a reason to ask that question before, your answer is probably something vague. Mines, the ground, rivers maybe, if you have ever seen footage of someone panning for it. Gold is one of those things that simply exists, embedded in rock somewhere, waiting for someone to dig it out. It is treated culturally and economically almost like a constant, something that has simply always been sitting in the earth in fixed deposits, waiting to be located rather than actively being produced by any ongoing natural process. I want to be honest with you, that was more or less my answer too, until I started reading about what a team of geologists has been piecing together, sample by sample, from the floor of the South Pacific Ocean. Because right now, at this exact moment, several kilometers beneath the surface of the ocean, in a chain of underwater volcanoes north of New Zealand, the Earth appears to be actively manufacturing gold, not storing it, not simply containing it, the way a vault contains something already finished, making it through an active, ongoing chemical process in real time, in a location almost nobody has ever had a reason to look closely at. This is not a metaphor, and it is not speculation from a single strange paper. It is the conclusion of years of careful sampling, laboratory analysis, and geochemical detective work, published in a peer-reviewed journal called Communications, Earth and Environment, led by a research team that spent decades collecting the physical evidence needed to make the case. And once you understand what they found, gold stops being simply a thing you find and starts being something you can trace, almost like a river, back to a specific process happening deep inside the planet, in a place we have barely bothered to look until now. Stay with me, because this involves melting rock several times over, a strange class of underwater glass that acts like a time capsule, and one very simple, very old question that geologists have argued about for years without a clear answer until now. Let us start with why this question was even worth asking in the first place. Around the world, geologists have long noticed something that seemed almost too consistent to be coincidence. Some of the richest gold deposits on the planet are found in a very specific type of geological setting, along chains of volcanoes called island arcs, curved lines of volcanic islands that form where one of Earth's tectonic plates is slowly sliding underneath another, a process geologists call subduction. If you picture the Pacific Ocean on a map, many of the volcanic island chains ringing its edges, sometimes referred to collectively as the Ring of Fire, sit directly above zones exactly like this. Japan, the Philippines, Indonesia, and stretches of the western coast of South America all sit along this same general belt, and many of the world's historically significant gold-producing regions trace back to volcanic activity connected to this exact style of tectonic setting. This is not a small or obscure category of geology. It represents some of the most economically significant gold-bearing terrain on the entire planet. And it turns out that gold deposits associated with these specific volcanic regions are, statistically, unusually rich compared to gold found elsewhere on the planet, including gold associated with other types of volcanic activity, like the volcanoes that form along mid-ocean ridges, the long underwater mountain chains where a new ocean crust is constantly being created as tectonic plates pull apart rather than collide. Two different styles of volcanism, driven by two very different tectonic settings, one where plates converge and one where they diverge, and one of them consistently produces far richer gold deposits than the other. Here's the part that had genuinely puzzled researchers for a long time. Everyone could see the pattern. Island arcs above subduction zones tend to produce gold-rich deposits. Almost nobody could fully explain why, in specific mechanistic terms, this particular geological setting behaves so differently from other volcanic environments on the planet. Theories existed, but direct physical evidence, the kind that could trace the actual chemical pathway gold takes from deep mantle rock into an eventual mineral deposit, remained frustratingly incomplete. To finally answer that question, a research team led by Dr. Christian Timm, a marine geologist at the Geomar Helmholtz Center for Ocean Research in Kiel, Germany, turned to one of the more unusual and useful natural materials available to geochemists working underwater: volcanic glass. Here is what makes volcanic glass so valuable for this kind of research. When lava erupts on land, it cools slowly, over hours or days, exposed to open air. During that slow cooling process, minerals inside the molten rock have time to crystallize, to reorganize themselves into new mineral structures, which means the original chemical composition of the magma gets scrambled and partially erased in the process. The way a photograph left out in sunlight gradually fades and loses its original detail. But when lava erupts underwater, especially at the depths where these particular volcanoes sit, it comes into contact with enormous volumes of cold seawater almost instantly. And the cooling happens so fast, sometimes within seconds, that crystallization barely has time to begin. The result is a natural glass, chemically almost identical to the original molten magma at the exact moment it left the deep earth, effectively a frozen snapshot of a chemical process that would otherwise be invisible to us, sealed and preserved the moment it made contact with the ocean. Researchers call the most valuable examples of this material primitive glasses, meaning they preserve the magma's original composition before it had the chance to change through crystallization or mixing with other material on its way to the surface. Finding and studying primitive glass is, in a real sense, as close as a geologist can get to directly sampling the deep Earth's chemistry without actually being able to travel there themselves. A substitute for a journey no one can physically make, tens of kilometers down into rock still hot enough to flow. Tim's team focused their search on a specific stretch of the South Pacific Ocean floor called the Kermadec Island Arc, along with an adjacent feature called the Havre Trough, both located north of New Zealand. This particular stretch of seafloor was not chosen at random. It sits along one of the more actively studied segments of the Pacific Ring of Fire, a region where the Pacific Plate is being subducted beneath smaller tectonic plates to the west, generating a chain of submarine volcanoes that had already drawn scientific attention for decades because of its unusually active hydrothermal venting and known association with metal-rich seafloor deposits. Over the course of 7 separate research expeditions conducted between 1999 and 2017, using a research vessel called the Sone, the team systematically collected rock samples from 17 distinct underwater volcanoes scattered across this stretch of seafloor. Collecting these samples was itself a substantial undertaking, involving dredging equipment lowered kilometers down from the ship, dragged carefully along the seafloor to pull up fragments of volcanic rock from specific carefully mapped locations, then hauled back up through that same enormous water column before the sample could even begin to be studied in a laboratory. In total, they gathered 66 volcanic glass samples suitable for detailed chemical analysis, a data set built up patiently across nearly 2 decades of expeditions before the full picture ever came together in a single published study. Here is what I want you to sit with for a moment. 66 samples, 17 volcanoes, 7 expeditions, 18 years. That is not a quick trip to collect a few interesting rocks. That is a multi-decade research program requiring repeated ocean voyages to a remote stretch of the South Pacific, all in service of eventually answering one specific chemical question that had been sitting unresolved for years. Many of the researchers who collected the earliest samples in 1999 were, by the time the final analysis was published, no longer necessarily the same people running the laboratory work decades later. This is the kind of science that outlives individual research grants and sometimes individual careers. A slow accumulation of physical evidence gathered specifically so that, eventually, someone would have enough material in hand to actually answer the question properly, rather than simply speculating about it. When the team finally analyzed these samples in detail, using instruments precise enough to measure concentrations in the big range of nanograms, meaning billionths of a gram per gram of rock, they found something that immediately stood out. The gold concentrations preserved in these primitive glass samples were, in Tim's own words, often several times higher than comparable magmas collected from mid-ocean ridges. The other major type of underwater volcanic system found across the globe. Let me try to put those numbers somewhere you can actually hold on to them. The measurements in these samples reach concentrations up to roughly 6 nanograms of gold per gram of rock, 6 billionths of a gram in a single gram of volcanic glass. That sounds on the surface like an almost meaningless amount, the kind of number that seems too small to matter. To put it in perspective, a single standard paperclip weighs roughly 1 gram. 6 nanograms of gold within that same mass of rock is such a vanishingly small quantity that no instrument available even a generation ago could have reliably detected it at all. This measurement only became possible with modern mass spectrometry techniques, sophisticated enough to isolate and count individual atoms of a specific element within an overwhelming background of everything else the rock contains. But context is everything here. 6 nanograms per gram is not simply a small number in isolation. It is a small number that is nonetheless several times larger than what turns up in equivalent samples from mid-ocean ridge volcanoes the baseline researchers use for comparison. In geochemistry, where you are tracking the movement of a genuinely rare element through unimaginably large volumes of rock, a multiple like that is the difference between a background trace and a meaningful, deliberate signal. The geological equivalent of noticing that one specific stretch of an entire river system consistently carries several times more sediment than every other comparable stretch, even though, on the surface, at a glance, all of the water looks identical. So the obvious next question became, why? Why would magma forming beneath these specific island arc volcanoes end up carrying so much more gold than magma forming at mid-ocean ridges? A completely different type of volcanic system, just a few hundred kilometers away in some cases. Are you still with me? Because I know the phrase mantle melting can start to sound abstract fast, the kind of term that slides past without really landing. Stay with me, because the mechanism the team uncovered here is genuinely one of the more elegant explanations I have come across in reading about deep earth chemistry. And once you see it, the whole picture snaps into focus. It also happens to solve a puzzle that, until this study, had left 2 entirely reasonable competing explanations on the table, with no clear physical evidence to decide between them. Here is the process Tim's team pieced together, based on the chemical signatures preserved in these glass samples. Deep within the Earth's mantle, the layer of hot, slowly flowing rock that sits beneath the planet's crust, gold does not typically exist as a free, isolated metal simply sitting there waiting to be released. Instead, trace amounts of gold tend to become chemically locked inside sulfide minerals, compounds formed with sulfur, which act almost like a vault, holding onto that gold and preventing it from moving freely through surrounding rock. Geologists sometimes describe elements that behave this way, elements with a strong chemical affinity for sulfur, as chalcophile, literally meaning sulfur-loving. Gold is one of these chalcophile elements, and so are several others the team specifically tracked alongside it in their analysis, including silver, copper, selenium, and platinum, all of which share this same tendency to bond preferentially with sulfur-bearing minerals rather than existing freely within surrounding rock. At subduction zones, where one tectonic plate is sliding down beneath another, that descending plate carries substantial amounts of water down into the mantle along with it, water that had been locked into minerals within the ocean crust and seafloor sediment over millions of years, absorbed gradually as that crust formed and aged at the surface long before it ever began its slow descent back into the earth. As that water is driven downward and eventually released into the surrounding mantle at depth, it does something specific and important. It lowers the melting point of the mantle rock around it, allowing that rock to begin melting at temperatures and pressures where it otherwise would have remained solid. Water, in this context, acts almost like a chemical key, changing the conditions under which solid rock will give way and begin to flow. Here is the key detail the team identified. This is not typically a single, one-time melting event. The data instead point toward repeated, multi-stage melting, meaning the same general region of mantle rock appears to undergo melting more than once in stages as conditions shift and additional water works its way through the system over time. Picture a sponge being squeezed, released, and squeezed again, each cycle pulling a little more liquid out than the last, rather than one single squeeze that extracts everything at once. And this is where the gold vault finally gets cracked open. Each time this hydrous mantle rock undergoes another round of intense melting, more of the sulfide minerals holding that trapped gold get broken down chemically, releasing the gold they had been holding onto directly into the surrounding molten rock. Do this once, and you release a certain amount of gold into the melt. Do it again on the same general parcel of mantle material that has already been partially depleted of other elements by the first melting event. And you concentrate the remaining gold even further into a progressively smaller volume of magma, because gold specifically favors staying dissolved in that melt, rather than remaining locked in whatever solid mineral residue is left behind. Each additional round of melting is working on rock that has already given up some of its other, less stubbornly bound material, which means the gold that remains becomes an increasingly concentrated fraction of what is left to extract. Tim described this using a phrase that has stuck with me since I first read it. He said the mantle beneath these island arcs behaves like a multi-stage melting system that progressively concentrates gold, a system, not a single event, a process that effectively cooks the same material more than once, each round driving the gold further out of its mineral vault and further into the rising magma that will eventually feed the volcanoes sitting above it. Here is what I find genuinely remarkable about this explanation, once you actually sit with it. For years, researchers had assumed that the water itself, being carried down by the subducting plate, was somehow the direct chemical agent responsible for pulling gold out and enriching the magma. Tim's own team initially expected exactly that, and said so directly in describing their results. Their data told a more specific and, in some ways, more surprising story. The water's real role in this process is not directly grabbing and carrying gold. Its role is enabling repeated melting to happen in the first place, by lowering the mantle's melting point enough to allow it to melt more easily, and more than once. The water is less like a solvent actively dissolving gold, and more like a key that keeps unlocking the same vault repeatedly, each time releasing a little more of what was sealed inside. This distinction matters because it explains something that had puzzled researchers for years. Not every subduction zone on the planet produces equally gold-rich magma, even though water is being carried down into the mantle at virtually all of them, since subduction by its nature always involves descending oceanic crust, carrying at least some hydrated minerals along with it. What appears to matter most is not simply the presence of water, but the degree, and specifically the repetition, of melting that water enables in that particular patch of mantle. Some regions may experience this multi-stage melting process more intensely or more repeatedly than others, based on the specific geometry, depth, and thermal history of that subduction zone, which would help explain why gold enrichment varies so significantly from one volcanic arc to another around the world, rather than appearing uniformly wherever subduction is happening. Two subduction zones can look broadly similar on a map and still produce dramatically different gold outcomes, depending on this less visible variable of how many times and how thoroughly the mantle beneath them has actually been cooked. I want to step back for a moment and make sure the scale of what is actually happening here is clear, because it is easy to let a phrase like mantle melting slide past without registering just how extreme the conditions actually are. This process is unfolding tens of kilometers beneath the seafloor in rock subjected to pressures and temperatures that do not have any easy everyday comparison. Rock that is simultaneously being pulled downward by plate subduction, infiltrated by water driven out of the descending plate, and melted repeatedly into magma that will eventually rise back up through kilometers of solid rock and erupt onto the ocean floor as the volcanic glass this entire study is built from. The sample sitting in a laboratory vial, a few millimeters of dark, glassy rock, is the end product of a journey that began with solid mantle material tens of kilometers down, melted and remelted, chemically transformed step by step, before ever reaching daylight, or, in this case, ocean floor light at all. Here is why this finding matters beyond simply satisfying scientific curiosity about a geochemical puzzle. Tim and his colleagues have effectively identified the very first step in gold's entire life cycle, the moment where gold begins its long journey from being an invisible trace element locked inside solid mantle rock, toward eventually becoming the kind of concentrated mineable deposit that ends up in a ring, a coin, or a bar of bullion. Magma that starts out already enriched in gold, thanks to this repeated mantle melting process, carries more raw material into the shallower systems above it, where later stages involving hydrothermal fluids circulating through volcanic rock closer to the surface can concentrate that gold even further into the kind of dense mineral deposits that mining companies eventually locate and extract. In other words, every rich gold deposit ever discovered near an island arc volcanic system, on land or on the seafloor, likely owes its existence, at least in part, to this exact process, happening kilometers beneath the ocean floor, long before any human being ever set foot anywhere near it. The gold in a wedding ring, or a gold bar sitting in a vault, may have started its actual journey not in a mine, but in a pocket of superheated, water-infiltrated mantle rock beneath an island arc volcano, melted and then melted again, until enough of it had been chemically freed from its sulfide prison to eventually make its way toward the surface. This also connects directly to a subject that has come up before in stories about the deep ocean floor, and one worth sitting with carefully. Regions like this, underwater volcanic arcs known to be unusually enriched in gold and other valuable metals, are increasingly becoming targets of interest for deep-sea mining companies and the governments backing them, drawn by exactly the kind of geochemical enrichment this study helps explain. Seafloor massive sulfide deposits, the dense, metal-rich mineral formations that build up around underwater hydrothermal systems in these same volcanic arc settings, are already being surveyed and, in some jurisdictions, licensed for potential future extraction, precisely because they concentrate not just gold, but copper, silver, and other valuable metals into deposits far richer than equivalent ore found on land. Understanding precisely how and why these deposits form is not simply an academic exercise. It has become directly relevant to real decisions being made right now about which stretches of remote seafloor might eventually be opened up to industrial-scale extraction, and which fragile, barely studied deep ocean ecosystems sit directly on top of the very geology that makes those locations so commercially interesting in the first place. The same repeated mantle melting process that quietly concentrates gold over geological time scales, entirely independent of any human activity, is now being read by mining geologists as a kind of treasure map, a set of chemical signatures that can help predict where the next commercially significant seafloor deposit might be sitting, waiting to be found. Let me bring this back to where we started, because I think the full shape of this story is worth holding in your head all at once. Gold, an element most of us encounter only as a finished object, a ring, a coin, a bar sitting behind glass, actually begins its existence as an invisible trace locked inside solid rock, tens of kilometers beneath the ocean floor. At specific locations around the planet, where one tectonic plate slides beneath another, water carried down by that descending plate repeatedly triggers melting in the surrounding mantle, and with each new round of melting, more of that trapped gold gets chemically freed from the sulfide minerals holding it, concentrating further into the rising magma. That magma eventually reaches the seafloor, erupts and cools in an instant into volcanic glass, a natural, accidental time capsule that, tens or even thousands of years later, a research vessel can dredge up from several kilometers down, carry back to a laboratory, and analyze with instruments precise enough to detect a handful of billionths of a gram. We did not know the specific mechanism behind any of this until a team of researchers spent nearly 2 decades collecting samples from 17 underwater volcanoes, patiently building toward an answer to a question that had sat unresolved for years. The ocean floor, it turns out, is not simply where gold sometimes happens to be found. In a very real sense, for a meaningful fraction of the gold that eventually reaches human hands, the ocean floor is where gold's entire story actually begins. I keep coming back to one detail in particular from this whole account. Tim described what they found as effectively looking at the first step in the life cycle of gold, not the discovery of gold, not the extraction of gold, the beginning of its life cycle, a phrase that treats an inert metal almost like it has a biography, a point of origin, a journey. And in this case, that journey starts kilometers under an ocean most of us will never see, inside rock being melted and remelted by forces that have nothing to do with human activity at all, following a process that has presumably been running, quietly, quite literally, cooking gold into existence, for as long as subduction zones have existed on this planet. There is something genuinely strange about holding a piece of jewelry, or thinking about a gold coin, and knowing that somewhere in its history, long before any human hand touched it, long before it was ever mined, smelted, or shaped, it existed as a scattering of individual atoms locked inside a sulfide mineral, tens of kilometers beneath an ocean, wading through repeated cycles of melting for a chemical process indifferent to human timescales to slowly concentrate it into something eventually worth extracting. We tend to think of gold as ancient in the sense of old, something humans have valued for thousands of years of recorded history. But the process that actually creates the conditions for a rich gold deposit to exist in the first place operates on a completely different scale of time and place. Running continuously right now, in volcanic systems most of us will never see even a photograph of, driven by tectonic forces that could not care less whether anyone above ever finds what they leave behind. The surface is not the whole story. It never was. If this documentary gave you something you did not have before you pressed play, if gold feels like a genuinely different substance to you now than it did 20 minutes ago, then subscribe to Abyss Files. Every week we go somewhere the surface does not show you. Every week there is something the ocean floor is still hiding. And I promise you, it only gets stranger from here.